Right. Let's talk about one of the biggest, most mind-bending ideas in all of science, Einstein's theory of relativity. I know, the word relativity can sound super intimidating, but stick with me here. I promise, by the end of this, you're going to have a real grasp on how this one idea completely flipped our understanding of space, time, and gravity on its head. So are you ready to have your reality stretched a little? Let's do this.
So here's how we're going to break it all down. We've got 4 main stops on our tour. First up, we're going to talk about a whole new concept for reality called spacetime. Then we'll get into the cosmic speed limit with something called special relativity. After that, we'll uncover gravity's biggest secret, and to wrap it all up, we'll see how these massive ideas are actually at work right in your pocket.
Okay, before we get into the heavy stuff, let me ask you something. Is time always the same for everyone? I mean, it seems obvious, doesn't it? A second is a second, a minute is a minute, no matter who you are or where you are, right? Well, what if I told you that's one of the most fundamental things we get wrong about the universe? Einstein showed us that reality is a whole lot stranger, and that's the door we're about to walk through.
All right, Section 1, a new fabric of spacetime. To even begin to understand Einstein, we have to throw out the old rulebook. For hundreds of years, we thought of space as this fixed three-dimensional box, and time was like a universal clock that just ticked away the same for everybody. They were two totally separate things. But Einstein's first big move was to say, nope, you've got it all wrong. They're actually two parts of the same thing.
He called this mashup spacetime, and that word fabric is so important. Don't think of spacetime as just empty nothingness. Instead, picture it like a dynamic, flexible, fabric that everything in the universe sits on and moves through. It's not just the background scenery for the universe, it's actually a key player in everything that happens.
So now that we have this idea of a space-time fabric, let's move on to Section 2, and Einstein's first masterpiece from 1905, Special Relativity. This theory really zooms in on one specific scenario. What happens when stuff is moving at a constant speed, especially when it's moving insanely fast?
Okay, so special relativity is built on 2 core ideas, or pillars. The first one is pretty easy to get your head around. It just says that the laws of physics work the same for everybody who's moving at a steady speed. You know, if you throw a ball on a smooth-riding train, it behaves just like it would if you were standing on the ground. Makes sense. But that second pillar, oh man, this is where things get weird. It says that the speed of light is the same for everyone, always, no matter how fast you're moving.
And just look at that number, 300 million meters per second. It's just staggering. And here's the absolute kicker. This isn't just some record we're trying to beat. It's a fundamental, unbreakable law of the universe. Nothing that has mass can ever reach this speed. It is the ultimate speed limit.
So this unbreakable rule creates a really bizarre problem, a paradox. Imagine you're in a rocket ship, blasting through space at nearly the speed of light, and you turn on your headlights. Common sense says that light beam should only look like it's creeping away from you, but that law says no. You'd still measure that light beam zooming away from you at 300 million meters per second. So how is that possible? If the speed of light is the one thing that absolutely cannot change, something else has to give, right?
The answer? Time itself. Yeah, you heard me. To keep the speed of light constant for everyone, the universe actually slows down time for things that are moving really fast. It's a real phenomenon called time dilation. A clock on that rocket ship would literally tick slower than a clock back here on Earth. This is the big reveal. Time isn't absolute, it's relative.
And it doesn't stop with time. Space gets in on the action too. To a person watching from Earth, that super-fast spaceship would actually appear to be squished, shorter in its direction of travel. We call this length contraction. So you see, space and time are this stretchy, flexible duo, and they bend and warp as much as they need to, all to protect that one unbreakable law, the cosmic speed limit.
And all of this weirdness is what leads us to maybe the most famous equation in the history of the world, E equals m squared. What this is really telling us is that mass and energy are just 2 different forms of the same thing. Mass is just an incredibly concentrated, bottled-up form of energy. A tiny bit of mass can unleash a mind-boggling amount of energy.
All right, let's head to Section 3. So special relativity was a total game changer, but it had a couple of big holes. It didn't have anything to say about acceleration, or, the big one, gravity. Einstein wrestled with this for another 10 years, and the result was his 1915 masterpiece, General Relativity. And it's a completely different story about what gravity actually is.
And this is the absolute heart of it. We all learned about Newton's idea of gravity, right? This invisible force that pulls an apple to the ground. Well, Einstein looked at that and said, what if it's not a force at all? He realized that gravity is simply what we experience when mass and energy bend and curve the fabric of space-time around them.
Now, I know that can be tough to wrap your head around, so let's use the classic analogy. I want you to picture space-time as a giant stretched-out rubber sheet, or maybe a big trampoline. When it's empty, it's perfectly flat.
Okay, now, let's place something really heavy in the middle of our trampoline, like a bowling ball. That's going to be our sun.
See how it makes a big dent, a big curve in the sheet? Now, if we roll a smaller marble nearby, that's the Earth, what happens? It starts circling around that big dip. It's not being pulled by the bowling ball. It's just trying to go in a straight line, but the path itself is now curved. And that path, that orbit, that is what we experience as gravity.
And this is where it gets really wild. This warping doesn't just affect space, it affects time too. The stronger the gravity, the deeper the curve in our trampoline, the slower time itself actually flows. And this leads to an absolutely bonkers but 100% true fact. Because your feet are just a little bit closer to the center of the Earth than your head is, they are aging a tiny, tiny, tiny bit slower than your head is right now. It's real.
Okay, section 4. So we've talked about some pretty out there concepts. Warped space-time, aging feet. You're probably thinking, this is fascinating, but what on earth does it have to do with my life? Well, the answer is a whole lot more than you might think. You are actually using relativity every single day.
Let's start with the GPS in your phone. The satellites orbiting the Earth are moving incredibly fast, which means their clocks tick a little bit slower. That's special relativity. But they're also in much weaker gravity than we are, which means their clocks tick a little bit faster. That's general relativity. If the engineers didn't precisely calculate and correct for both of those effects, your phone's GPS would be off by about 7 miles every single day. It would be useless. It goes on. Even electromagnets work because of these effects. And of course, the most extreme things in the universe, black holes, were predicted by general relativity, long before we ever saw one.
And this is a really crucial point. This isn't just some clever thought experiment. For over 100 years, scientists have been putting relativity through its paces, testing it in every way imaginable. They've measured starlight bending around the sun. They've detected literal ripples in spacetime from colliding black holes. And every single time, Einstein's equations have been proven right. It's one of the most solid, well-tested ideas in all of science.
So, when you boil it all down, what's the big takeaway? It's that the universe is so much weirder and cooler and more fascinating than our everyday senses tell us. Over a century ago, one person's incredible curiosity completely redrew our map of reality. And it just makes you wonder, doesn't it? As we keep looking out into the cosmos, what's the next mind-blowing secret the universe has tucked away, just waiting for the next curious person to find it?